All right. So today we start with chapter 6, which is on the use of entropy. I realize that chapter 5 is a rather difficult one, quite theoretical. Now let's make use of what we learned there closer to practical systems. So up to the point, we have been concerned primarily with what the word entropy means about thermodynamic cycles. What we want to do here is we want to use this concept to analyze thermodynamic systems, to integrate the second law of thermodynamics into the analysis. So this is what I said here. So essentially, I want to remind you, though, that entropy is as fundamental a concept as internal energy was. The conservation of energy principle, that is the nature of the first law. The maximization of entropy as systems tend to go to equilibrium, that is the second law. These really are the two fundamental concepts. And in practice, if we go to statistical thermodynamics, for example, we will, in fact, define all other properties, pressure, temperature, whatnot, as a function of both internal energy and entropy. And all the other thermodynamic variables are derived from those two. So these are the two fundamental properties. Of course, entropy is much more abstract than energy, and it is harder to understand. That's why we spent quite a bit of time on it. Understanding was chapter 5, using is chapter 6. So this gets me to our lecture 14 on chapter 6. I will review again from chapter 5 the concept of entropy balance and the concept of Clausius inequality. And then we will define entropy change and explain to you how to retrieve these entropy data. So entropy essentially, what we learned last time, has two properties. If you consider the part of it that's the equation of state, which we call S, that is something that we can study the change of, and we can use the entropy data. There is the other part that represents the irreversibilities that we call sigma, which of course you cannot get from the data. That is something that you have to get otherwise in your problem. So let's go a little bit through the review of what we did before. Like mass and energy are extensive properties of the system, entropy is an extensive property of the system. Like mass and energy are accounted for by balances, entropy has to be accounted for by a balance as well. And here is that balance. The change in the amount of entropy contained within a system during some time interval equals the net amount of entropy that is transferred in or out of the system across the boundary in the same time interval. But then this is new. And then there is an amount of entropy produced within the system during the time interval by the irreversibilities in that system. So only here, this equals this, only in the case of perfectly reversible systems, Carnot cycles, for example, but any real system has this additional term. And so in this equation, only the transformation in here, that change, can only be gotten out of tables if you know the net in and out. The tables can only cover this. They cannot cover that. That is something you have to get externally. So, like mass and energy, entropy can be transferred across the system boundary. For closed systems, the entropy transfers are accompanied by heat transfer, just like we had for internal energy. When you have controlled volumes, entropy transfer can occur by heat transfer, but also by entropy that comes in and out of the system through streams of matter, just like we did. So just like there's a workflow theorem, there is an entropy theorem. Now, unlike mass and energy, that didn't have this third term, entropy has a third term, which is the entropy produced and generated by non-idealities or irreversibilities in this system. Okay, so let's review the Clausius inequality, which states, it's a consequence of the second law, that states that for any thermodynamic cycle, the integral over the cycle of the quantity dq divided by T as exchanged through the boundaries has to be smaller than 1. So in here, dq is the heat transfer at the system boundaries. T is the temperature in absolute value in Kelvin, as we defined it last time. This integral is taken over the cycle, and this subscript b denotes the fact that the integrand is evaluated only over the boundary of the system. This is not a volume integral. This is an integral only over the outer volume of the system, outer surface of the system. So, Clausius inequality is a corollary of the second principle, and the equality, the equal sign here, applies only to cycles that have no internal irreversibilities, which are cycles where the compression is ideal and the expansion is ideal with no losses, no frictions of pistons or turbine blades or whatever. And it also happens when heat transfer is happening with no finite temperature differences. This is, of course, not possible. You need a temperature difference to drive a heat transfer, so this is never ideally obtained, but it is the ideal situation where there are no ideal irreversibilities. And that's when you have the equality. The inequality, so this is negative, applies to all real systems because you always have irreversibilities, though our task is to engineer these irreversibilities to be as low as possible. Let me then refine this. We derived in the last class that because we have to keep delta as, well, we defined in the last class that this is the term that defines the first two ones across the boundaries. So the two reversible terms, whoops, these two are defined by the quantity here, and the irreversibilities is the sigma of the cycle. I'm just expressing the exact same idea as we had before. So when the sigma of the cycle is 0, there are no irreversibilities. Most of the cases, real cases, the sigma cycle is positive, and this is impossible, excluded by the second principle. We do that because then if the cycle is ideal, with no irreversibilities, this is 0, integral over the cycle is 0, which then means that this quantity, delta Q over T, is an equation of state. We like equations of state because we can look them up in the tables. So the reversible part, which is this, setting that to 0, is then defined by transformations across a process. So equations of state, the process between 1 and 2 of the integral of this dq over t, if the system is reversible, gives you the difference between entropy in state 2 and state 1, which is what we can look up. So I repeat, the reversible part is defined by S2 minus S1 is integral 1 of 2 of this quantity, dq over t. That equation is defined, the entropy change for all processes, for any process between two states. But of course, it's only definitely the total entropy if the processes follow the reversible transformation path. This then is an extensive property, as I have said so. The unit in SI units is in joules per Kelvin. Often it's in kilojoules per Kelvin. And in English units, USGS, it's BTU per degree Rankine. Notice that we use absolute temperature scales here. Now, entropy, just like its brethren, can be defined on a specific base. Per mass base is lowercase s. Per mole base is lowercase s with a bar above it. Per mass base, it is kilojoules per Kelvin kilogram, or BTU per pound per Rankine. I review again this concept of entropy change. So if we go from 1 to 2 through the reversible process, we have S2 minus S1 is this delta Q over T for internal reversible process, which means that if I have a reversible process between A and B and I come back, I have then a net entropy change between 1 and 1, that is 0. Any cycle, though, can go through one way and come back through another way that is irreversible. So if it is irreversible, we have this extra entropy due to the irreversibilities, and this part of it is only defined in the ideal reversible cycle that undergoes the same amount of heat and work exchange. So this would then be the entropy added or removed through the boundary, where this is the part that reflects the irreversibilities and therefore must be positive because that has to be zero and that has to be negative. Now, we cannot use this integral if the process is irreversible. I showed that last time and repeated another time. This is wrong, simply wrong. There we go. Entropy is an equation of state and therefore can only be defined on the reversible path between the initial and the final state. So you have to find your reversible path, then you can derive your entropy change, and that is an equation of state if you go through a cycle. Now, we will define this. If you have an irreversible cycle, we will define it as a reversible cycle value, and then we'll correct. All right, so now if you have this cycle, this reversible cycle of transformation, you have states 1 and 2, where do we find the quantities capital S? I repeat, you cannot find sigma, but you can find capital S. Well, we introduced ways to retrieve data from tables, from graphs, equations in the book. We did that for pressure, volume, temperature, internal energy, and enthalpy. To this today, you add that you can also look up in the same books the value of entropy S, or S lowercase s per kilogram, or lowercase s bar per mole. So this is defined as a state property, and you need two intensive variables to find it in your tables, just like you do with all these others. If you know two of them, you can find all the others. Just add S to this line, and you will understand how the system works. So if we have a PVT system, we can find S of P and T, S of T and V, S of P and V, and so on and so on, just like we did before. So defining this equation for entropy change with the concept it has to only be defined on a reversible system. That is the basis for evaluating the entropy relative to reference value, because we calculate differences. Now, the use of entropy values relative to this reference state is unambiguous, as they are used inside calculations for differences and within the same table. But entropy is relatively easier, in fact, in this case, than enthalpy, because the reference state vis-a-vis temperature is well defined, which was not the case for the enthalpy or the internal energy. That was arbitrarily defined. Here it is defined by the absolute temperature scale. Now, in pressure, that is not so. When you take a change in entropy vis-a-vis pressure, that starting pressure is arbitrary. So let me then give you the Nernst principle, which sets the definition of where entropy is zero. At T equals 0, entropy must be 0. That is almost as strong as the third principle of thermodynamics. So if you're going to be looking for an entropy change with temperature, then S at your point F is S at the point reference, integral from reference to F of dq of T. If the reference if T is the only thing that varies, the ref in T is at T equals 0, and then this term is necessarily 0 by definition, actually by the third principle. Now, if you retrieve your tables, you can find them for water and steam, just like you did with enthalpy. They're tabulated specific entropy versus per kilogram or per mass, or you can have it per mole as well. Now, if you are within the vapor dome for states between the saturated liquid and saturated gas, then you calculate your entropy by interpolating using the quality X of your mixture of steam and of your mixture of vapor and liquid. So S at a certain state then is 1 minus X S at the saturated liquid plus X times the value of the saturated gas. This is the same equation as we had for enthalpy and internal energy. In EES, if that's what you use, you can write it exactly the same way as you did with enthalpy and internal energy. You just write entropy. So, to give you a few ideas of how this is done inside a PVT system, if you are here inside the vapor dome, what you do is what I told you before. You interpolate vis-a-vis X using the interpolation value, then is the quality of your steam, which is defined. You can derive X when you know the values of entropy, just like you can derive X when you know the values of enthalpy or internal energy. So these equations are exactly similar to what we had for specific volume. If, on the other hand, you are in the incompressible fluid, so here, where we used to have the specific volume is only a function of temperature and not of pressure, and therefore that if you want to look specific volume here, all you have to do is look at the equivalent value. Here, the saturated liquid line, and internal energy the same, and enthalpy, a little correction vis-a-vis pressure. Well, it's the same thing for entropy. Entropy in this part of the phase diagram is just the entropy at the saturated liquid line for the same temperature. Now, for the ideal gas, things are much more complicated. So ideal gas was very comfortable as long as we had enthalpy or internal energy, because they were functions only of temperature. Not so entropy. Entropy also depends on pressure, and that gets a little more complicated. We will get a whole lecture on just that. Thank you.